Okay, Assalamualaikum warahmatullahi wabarakatuh and a very good morning. Berjumpa lagi kita di kuliah kita yang kedua on our kuliah lah. This is already week 4 week 4 week 3. So I think on our last kuliah we already cover for chapter 1 for the subject mechanic of machine DJJ40163. We already covered chapter 1, which is the hoist. Now, of course, for the chapter 1, we also cover some examples and a tutorial on how to solve it. How to calculate all those problems that related to the hoist structures and mechanics. So now, for our current kuliah, for our current lecture, we're going to proceed with chapter 2 with title of Simple Harmonic Motion. Okay, this is a very important thing since simple harmonic motion is one of the good pointer for to solve this kind of problem. And all the problem that related to the motions and all the problem related to the mechanics somehow they solve it throughout this method or this approach, which is we call simple harmonic motion. Okay, so this is kind of like introduction, some of introduction. I'm going to for this period, for this current lecture, what we're going to do is I'm going to deliver all the lecture, then we're going to finish up with some examples. They got a couple of examples, at least four to five examples at the end of the lecture. So more or less the student is expected to learn and understand the fundamental of the subject lah, yeah. So this is some brief of example or for introduction part. So for the simple harmonic motion, just consider a particle P moving around the circumference of a circle in an anti-clockwise direction with a constant angular velocity omega. Okay, so you just try to imagine, consider a P moving around the circumference of cylinder. Oops, sorry. Wait up. Wait up, yeah. I got some issues with my things. Okay, no worries. Just proceed. Okay, let's say we got some what you call it, a circle of shape. Okay, and then it moving from X to Y, and then N is moved from X to O to 0 basically. And then for the B case, it got Y to X, which is this one is X prime. When N move from 0 to X prime, and so on and so forth. Where it clearly stated here, P completes one revolution and N complete one vibration about point O. The motion of N is known as simple harmonic motion. You can see here. Okay, this is simple harmonic motion. Yeah, either it move to X prime or it move to Y prime. It doesn't matter. All right. So same goes like this case. Yeah. Okay. So same goes like this case. So from point 0 to N1, which is the movement is, the distance is X1, and then it goes up to P1. So you know this is the distance and this is the distance. Okay, this is more or less similar to like vector. Okay, So same goes with this case as well for P2. So what you can see the difference where if you compare between these two cases, okay, for X1, the distance is quite larger than in comparison to X2. Yeah, X1 is more greater in terms of distance compared to X2. Okay, since the distance to reach N2 is quite short. Okay, yet the P is much more, the P2 is much more higher, the distance from P2 to 0. Okay, distance from P2 to 0 is much more higher compared to the first case. Okay, so we go by the third case. Same goes like, for the P3, the distance from P3 to 0 is much more higher. And if we compare from 0 to N3, the distance is X3 lah. Okay. Let's say if this P3, if this point is swing to be much more lower at this stage, let's say P3. So what will happen? Okay, the distance of N3 would be much more greater. Okay, and the distance from 0 to this new position is also going to be much more greater. Right? This is some example that show. All right. For this case, basically the distance is the radius of the cylinder circumference. Cylinder circumference, yeah, the distance of it. And of course, you're just going to finish all the loops. Okay, let's say for the P5, in the position of P5, if you measure the distance from 0 to P5 is, let's say you got some values here, yeah? You got some values here, which is we don't know. Yet, at this point earlier, the distance from 0 to X is a radius of the circle of the cylinder. I mean, of the circle. Yet, if you move it to P5, X5 is much more shorter. Okay, and then it all move out. Let's say if it goes here, and then the distance will be X6 would be R radius. Okay, so this is something that you need to understand. You need to have a grasp of it. Yeah? The fundamental of the mechanics itself. Okay, something like this. Okay, so basically the movement and the motion of the position. Let's say P1, P2. My goodness, P2, P3, P4 is all determined by the motion, which is we call as a simple harmonic motion. Okay, this is a fundamental of simple harmonic motion. Of course, this kind of mechanics can be found clearly in our daily practical life. As in industry itself, in dealing with this harmonic motion, basically we deal with the machine that vibrates. Machines that vibrates, maybe a pulley, maybe a rotor and shaft, maybe a flange, something like that. So once it operates, once the machine is operates, what happen? Basically, we're going to produce in amount level of vibration. So you're going to have some vibration there. So we as engineer, what we need to do, we need to evaluate the structure to see either it can withstand with the vibration or not. If we couldn't if the structure couldn't withstand with the vibration, then it's about time to replacement, some some schedules maintenance and so on. You need to schedule some maintenance, right? So for replacement of a compartments or parts for the structure. Of course, a crankshaft, if if you commute from your place to the office, or from your place to the, what you call that, to the classes and so on. Of course, to be fair, there's a lot, the great amount of structures that dealing with this kind of problem. Simple harmonic motion. You can go with your free wheel, you can go with your shaft, crankshaft, and so on. So this is basically the fundamental of harmonic motion. Okay. Here, I got some example. I'm going to elaborate more about some example. Basically, I'm going to point out three examples basically what's stated throughout the presentation. The simple harmonic motion is a repeated motion with a particular frequencies and period. Frequencies is the measurement value of the vibration, getaran itu sendiri, ya. And period basically is a time. Okay. So how long it take for the structure to vibrate in the function of frequency. How many seconds it going to take for it to complete a movement, for it to complete what you call that, a rotation, for example. Okay. So for this case, basically, it show three cases for to represent a simple harmonic motion. Basically, we got vibration tuning fork. This one basically, let's say, uh, if you want to measure some vibration, if you want to check, basically, more better to check. If you want to check if there is a vibration around the machine or whatever. So while the machine is operating, of course, while it's operating, it's going to a bit shaking here and there. It vibrating lah, it's bergetar. So what you do is, let me just, okay. Let's say this is a machine lah. Okay. So it's shaking, the machine is rotating and it's shaking. So while it's shaking, to know if the machine is shaking severely or not, then you're going to have a vibration tuning fork. You bring it closer to the machine, and then if it if it follow through, it also vibrating as following the vibration of the machine itself. So basically, we're going to measure. They got some device to measure how many how many decibel it goes, or how many hertz that we need to know in order to inspect the machine. Other part of it, another example, we can say, let's say a guitar. We got a guitar. Okay, this is a very simple guitar lah, yeah. Okay, while you strumming the guitar, you playing the guitar. Of course, the strings itself, the string will be vibrating. So the vibration tuning fork, if we bring it closer to the guitar, it also going to vibrate, follow up the vibrating of the string. So from there, you're going to put all your devices, and then you're going to read what is the decibel of the sound, and how many hertz does it going to produce. This one we call it another topic lah. Basically, it's a vibro acoustic. Vibration acoustic. This one, if I may to elaborate more, let's say if you are kind of like engineer that you want to design what you call that, a philharmonic orchestra kind of, they want philharmonic orchestra, and then of course you want to make it comfort in terms of hearing of the orang yang datang lah. Okay, so what you need to do, you have to delicately, you have to carefully design the dewan harmonik tu to be selesa kepada orang yang mendengar. Jadi the sound cannot be melantun lah, because we know the sound is coming from the acoustic. So the acoustic level of the room need to be at par to what been outlined by DOE, Department of Environment. So of course they kind of having some, what you call that, they have some kind of like regulation which stated for a room that can, that can fill up about 40%, maybe 100%. So the vibration, the acoustic level need to be in whatever level it's supposed to be, whatever decibel it's supposed to be. So that one going to be much more better lah. If not, we cannot stand, our ears cannot stand with that kind of vibration sound. So it's kind of irritating. So that's why acoustic engineer, they kind of dealing with that kind of problem, where they're going to design a very ample and sufficient vibroacoustic for what you call that, for whatever thing that we designed it lah. That one is vibration tuning fork. Another case is a weight on spring. This one is very, what you call that, it's a very classic case, a classic case of simple harmonic motion. Basically, this is the spring where you got a mass, that the spring that needs to be supported by the spring. So the mass basically having a motion of downward and upwards. So while it keep moving up and down, of course, you're going to have this kind of motion. Okay. This is another classical example of simple harmonic motion. Another case is a boy on a swing. Okay, let's say this is the one. This is the swing lah. This is the boy lah. Dia duduk. So you're going to swing here up until here, from point A to point B, and then in the natural axis is a point 0. So same goes, it swing it to point A, then swing it to point B, and keep on until the kinetic energy is depleted. So if we manage to measure that kind of motion, so it's supposedly going to give us this some kind of, it's supposed to give us some kind like motion like this. So this is very common lah. Of course, we don't want it to be much more, of course, we want to control the motion, in order to avoid it to be severe or excessively, move the excessive movement that going to lead to the failure lah. So we need to control it a bit. So maybe you're going to damp it a bit, damp. You're going to damp it a bit. Maybe you're going to taruh pemberat sikit ke. Kalau you taruh berat dekat mesh, dia akan move lagi jauh. So mungkin you akan stiff, you're going to stiffen the spring, something like that. Okay, so this is the whole idea about simple harmonic motion that relatable to our daily life lah, Okay. On our second half of the topic, basically I'm going to elaborate more lah. I'm going to discuss more about the simple harmonic motion. So simple harmonic motion can be understood in terms of can be understood in terms of displacement, velocity, acceleration, and force vector. And of course, as is stated here, as you can see, it's related to the circular motion. Basically, simple harmonic motion, let's say, okay, this is a simple, this is the circle. So it's about the displacement, yeah, the velocity, and the acceleration, and the force vector. The force vector from here lah, the force vector that related to circular motion. Okay. And the point here is stated that recall that the displacement vector for circular motion is the radius of the circular path. The velocity vector is tangent to the circular path, and the acceleration vector always point towards the center of circle. Something like that lah, ya. The velocity vector is tangent. Dia bertangent to the circular path. Dia bertangent dengan circular path, and the acceleration vector always point towards the center. Acceleration tu akan point towards to the center of the system lah. Okay. So this is some definition lah, ya, terms of reference for our case. So as I mentioned earlier, basically for this topic, we're going to deal with the structure that move in the cyclic motion lah, ya. Alright, from the figure, you can see the equation here, x equal to r cos theta. What is r? Basically, r is the radius. Theta basically is the angle. Okay. And x is the displacement. Jarak ni. Okay. Omega is the angular velocity, kelajuan. Okay. And t is time. Therefore, the equation above give some displacement of point N from the center of circle. Here, from the center of circle, you're going to give some distance or displacement here, which is x equivalent to whatever value is supposed to go lah. Okay. It's a very clear, straightforward kind of formula. Okay. If equation x is equivalent to r cos omega t, and differentiate with respect of t. So let's say if we differentiate dx equivalent to r cos omega t, and then with respect of t, in the function of t, basically what we got is the velocity in terms of linear motion is equivalent to r omega sin omega t, or omega r sin theta. Okay. Okay, that here clearly show the negative sign shows that with an increase of x distance from the center to circle, the velocity decrease, it will be ignored after this. Yeah. So r means the velocity is decreasing. Okay. From the figure, you can see it stated that r sin theta equivalent to np equivalent to square of r squared minus x squared. Okay, in the square root of. Okay, so v equivalent to omega square root of r squared minus x squared. So w, oh sorry, it's not w. So omega is the velocity of the circular motion, r is the radius, x is the distance. And obviously, if you can see here clearly throughout observation, we can see that radius, the value of the radius is significantly different with the value of the distance. Okay, it's quite different in terms of for this case lah. Okay. So I'm going to proceed for another for the next slide. Yeah. So here we're going to find the maximum velocity. Okay, the velocity is defined as a maximum when x equivalent to 0. Here, this is the velocity lah. Okay, and still be here up until to the top. It called displacement, and then from 0 to here is called velocity. Okay, means you, I think to be fair, you don't have the distance lah. When x equivalent to 0, you don't have the distance. Then you got the velocity maximum. Okay. So V is equivalent to omega the square root of r squared minus x squared. Yeah. While for the case of V max is equivalent to omega multiplied by the square root of r squared minus since we know x is 0, the distance is 0, so we can cancel out. Yeah. So this one we don't have lah, since we know that x is equivalent to 0. All right. So we're going to form in terms of this equation, which is V max equivalent to omega R. And then, of course, we're going to do, this one is the velocity, and then we're going to go to the acceleration. All right. So we're going to differentiate the velocity equivalent to R omega sin omega t with respect of t. So very simple one. You know, you're going to derive it, you're going to differentiate it, then it turns out to be acceleration is equivalent to omega squared multiplied by x, which is x is equivalent to r cos theta here. It's the same thing, basically. Okay. Eventually, if you manage to get omega, then you have to square it in order to get acceleration. And then, of course, we know the maximum acceleration is equivalent to omega squared multiplied by r. Yeah. Why? We know velocity, the maximum velocity is here. Yeah. Velocity maximum. Maybe I presume the subhanallah. Maybe I presume the uh, maximum acceleration is supposed to be at this common position. So that's why, yeah. So that's why they don't have uh the what you call that, the sudut, or the angle is 0. And there's no angle here. So that's why it turned out to be this equation. Okay. We already covered some of the, I think, the very good definition of the physics. Yeah. So I'm going to proceed with the amplitude. Okay. What does it mean by amplitude? Amplitude is the maximum displacement of the north of the point N from it means position. And then another point is basically amplitude is the maximum displacement. Is the maximum displacement is equal to radius of the circle. Okay. So let's say if we got a circle, so this one is your 0. So this one is the radius. So from point here to point here, you can say is a displacement maximum. Okay. Then which is this one is equivalent to what? Is equivalent to amplitude. Okay. Oscillation is the movement. is the motion of n from x to x prime and then back to x prime to x. Okay, so just imagine like this. Okay, very simple one. And this is 0, so you got x, and here you got x prime. So it moving from x to x prime and back to x. Back to x prime and back from x prime to x. Okay, so it moved from this point, or it moved from, oh, sorry, it moved from this point to this point and then come back. That is what you call oscillation. Yeah, a motion of oscillation. And here is some equation that you call periodic time, where time for one complete cycle. As I mentioned earlier, this is time, and this is whatever motion, distance, everything. What our interest for this case is the period of time. So time to complete a cycle. So from point here to point here is a complete of cycle. That's why we put 2 pi. Yeah, just this one. If you overlap this point to this point, you're going to form a cycle, a circle, basically. Yeah. And frequency is the number of cycle per oscillation in 1 second. Let's say this one is 1, 2, 3, and then per 1 second is the number of cycle per oscillation. Okay. So the formula is n equivalent to 1 over t. Okay. All right. We're done with the theoretical part. Yeah. Maybe the theoretical part is something new to you guys, which is I don't believe so. You already learned it throughout the subject of mechanics previously. So this is just an extension of the mechanics subject, and it somehow relates to the machine subject. So it's not that difficult as you thought. A very simple one. Here we can see some example. Yeah. Okay, it shows here a piston of steam engine. Okay, a piston of steam engine moves with simple harmonic motion. Okay, the crank rotates at 120 RPM. Okay, rotation per minute. That what it mean by RPM. Rotation per minute. 120 rotation per minute with a stroke of 2 meters. The crank rotate 120. The pusing 120 pusingan per minute with a stroke of 2 meters. Find the velocity and acceleration of the piston when it is at distance of 0.75 meter from the center. So let me highlight first what they want you to find, what they want you to calculate lah. Find the velocity. We need to find the velocity lah. Okay, fair. And acceleration. They want to find the velocity and acceleration of the piston. What is the subject that you want to find? The piston, velocity, and acceleration. So to be more clear, to be more precise, this is your piston. Yeah, very clear piston. So they want to know what is the velocity and what is the acceleration that we don't know. So this is the piston lah. It got crankshaft here lah. It rotating. Okay. So a very clear one. It gives you some example here. If I can point out, it gives you 120 RPM, which is the rotation of the crank. the rotation of the thing crank up the what you call that the subhanallah that crank up the piston. Uh, so as we know, omega, the formula is 2 pi n over 60. Yeah, this is the formula 2 pi n over 60. Why 60? Because RPM per minute. Yeah. So basically, you manage to get 4 pi radius per second, which is your n, like which is your angular velocity, which is your w. Okay, pi is equivalent to 3.1482 multiplied by 4, and then 2r is equivalent to 2 meter with a stroke of 2 meters so 2r is 2 meter, means 2 meter is diameter of each stroke. Kena faham tak stroke tu apa? What does it mean by the stroke? You have to understand. This is thing that crank the shaft. This is the piston, and of course, this is the cranker, the crank. So if it move, clockwise, so it move on the right direction. It move here. Okay. Full stroke is 2 meter, means it goes full stroke. So that's why have a diameter of 2 meter. Because supposedly 2 stroke here, it move also 2 meter. Okay. So basically what you got here now is 2r equivalent to 2 meter, and then the radius is 1 meter, and then we got the distance is 0.75 meter. Okay. Okay. Here is the condition lah, yeah. Full stroke is moving downward, and then this is moving upward. Okay. Of course, we know this one supposed to crank in the angular motion. In order to make the piston moving in the linear motion. Okay. So here we can see a very simple equation. Velocity of the piston. Velocity is equivalent to omega multiplied by square root of r squared. Subtract with x squared. So by equate all the relevant, all the relevant values or parameters that already been stated throughout the questions. So you manage to get the velocity to be 8.31 meter per second. Yeah. So this is the velocity of the system. And the acceleration of the piston is A equivalent to omega power of 2 multiplied by x. So you got 118.46 meter per second squared. And of course, we know with find the acceleration or the maximum acceleration, there won't be any sudut tu. They don't have the sudut if you want to find the maximum acceleration. There will be no tak ada sudut lah. Okay. So here is example number 2. For example, number 2, it clearly stated here, a body moving with a simple harmonic has an amplitude of 1 meter and period of oscillation of 2 seconds. What will be its velocity when acceleration is 0.4 second? Okay, so what they want you to calculate? They want you to calculate the velocity and again acceleration. They want you to know, they want you to calculate, and they want to know lah what is the velocity and acceleration of the system. Okay, so they already given you lah, yeah. The amplitude R is equivalent to 1 meter. Period of oscillation is this kind of formula. What is the period of oscillation? Basically, wait up. You can see here very clear. This is time. So this is 1 and this is 2. So maybe it goes by this and this. So this is the period of oscillation. Okay. The period of oscillation is 2 seconds, and time taken for the body, time taken by the body from the extreme position. So maybe the body will be in the extreme position, maybe here lah, I think. 0.4 second. Okay. So how they solve it? Right, to find the velocity, of course, the formula is negative. So why is negative? Negative shows that the period of the velocity. So omega, how to find the omega first? Here. Okay. T equivalent to 2 pi over omega, and then of course you want to know the omega, you just rearrange the equations, and then 2 pi over 2, then you got 3.142 radian per second. Okay, why? Because you can cancel out. Okay, so this is the omega, and then omega you're going to multiply with r sin and omega t. We know r is 1. Yeah, r is 1 meter. If we stated here. Okay, sin pi multiplied by omega multiplied by t. We know omega is is a pi. Is a so when everything is here, of course you need to convert lah, yeah. Sin wt need to convert from rad to degree. Okay, so you just equating out, then you got 2 about 3 meter per second lah, 2.988 for the velocity. Okay, and then acceleration is very simple lah. This is the formulation, and you're going to equate everything, insert everything, and then you manage to get -3 meter over second squared. So this one is the acceleration lah, yeah. Okay. Okay. All right. Here is another example lah, yeah. Same goes lah. A piston of engine move with simple harmonic motion. The crank rotates at 100 RPM and the stroke is 150 cm, 180 cm. Okay. Find the velocity and the acceleration of the piston where it is at distance of 60 cm from center. So basically it seems like the first example. You know, just equate all the needed. Okay. You got the omega and then the stroke of piston. you know, amplitude slope here. All right. So displacement from center, you just turn out from cm to meter, and then using the equation, everything, then you manage to get WT equivalent to cos power of -1 multiplied by 0.667. Yeah, basically you want to find this one. Okay, and then the velocity is 7.02 meter square meter over second. This one is velocity, and then this one is the acceleration. I think, to be fair, all the this topic is quite straightforward, like, yeah, very straightforward. And what you need to understand is to know the definition and the terms, and where all the things, how it label and where it works. And then knowing some equation here and there, I think you can solve the problem. Very clear cut. Okay. So here is another example. Example 4. In a mechanism, a crosshead move in a straight guide with simple harmonic motion at distance of 125 millimeter and 200 millimeter from its mean position. Kedudukan asal. It has velocities of 6 meters over second and 3 meters over second, respectively. Okay. Crosshead move in a straight guide with simple motion. Okay. It has a velocity of 6 meters per second and 3 meters per second. Okay. Find the amplitude, maximum velocity, and the period of vibration. If the crosshead weight 2 Newton, calculate the maximum force on its direction of motion. Okay. Basically, the subject is a crosshead lah. One subject only. Move as it does it move lah. It move in the linear motion, either up and sorry. Yeah, sorry, my bad. It move either of course it move in a linear motion, but we don't know either it move, or horizontally or vertically. It doesn't matter. But it gives you two distances, from 125 millimeter to 200 mm, and of course it gives you two values of velocities as well. So they want you to find what they want you to find the amplitude, the maximum velocity, and the period of vibration. Okay, this time they give you one a new parameters. Eventually it give you the crosshead weight, which is weight about 2 Newton. So they want you to find the maximum force in the direction of motion. Okay. So here are some solution of it. So with the first distance, okay, 0.25 meter, we got velocity of 6 meter per second. In the distance of 0.2 meter or 200 millimeter, we got velocity of 3 meter per second. Okay. Okay, now we got a definition of R equivalent is the amplitude, and T is the period of vibration. So we solve it one by one. For X1, or the first distance, which is 0.25 meter, and here. So we just insert it into the equation. Okay, in order to find Yeah, the velocity, the angular velocity. Okay, so this is one thing. Of course, we don't know R lah, for sure. And another motion is, for the case of 200 mm or 0.2 meter, with velocity of 3 meter per second. Okay, so this is what you got. And we know R will be always the same lah. That's why you need to find the R. So we can equate these two equations together in order to find the omega and R. Okay, same goes like this lah. They basically they divide it. Okay, they divide it and then something like this lah. Yeah, 6/3 is equivalent to 2. So they go by here, squaring both sides. Okay, look it up. Okay, and then solve it throughout some, using mathematics basically. So you manage to get R equivalent to 21.64 meter, the radius. Yes. And then of course you're going to put R into this equation, then basically you're going to get the velocity, the angular velocity of the system is 33.33 radian per second. Okay. For the period of vibration, since we know T equivalent to 2 pi over omega, then we managed to get it. The movement is going to take about 0.19 second per period. And then the maximum velocity, V max equivalent to omega R, and then we're going to get 7.31 meter per second in the negative direction lah. Why in negative direction? Because as it stated clearly, the velocity is acting towards the 0. Okay. So this is a thing like I believe we need to go more details for this chapter 1, topic 1, simple harmonic motion. I believe on this Thursday, another class we're going to go through lah. We need to go through lah. To do more tutorials and example to get your fundamental understanding to be better lah. So everything can be asked during Thursday class. At the same time, I'm going to strengthen or empowering the first topic as well. Okay, on this coming Thursday lah. Okay, so up until now, I think I'm going to end my class now. So good luck and thank you. Assalamualaikum warahmatullahi wabarakatuh. Wabillahi taufiq wa hidayah. Assalamualaikum warahmatullahi wabarakatuh. Bye bye.